So in this video, I will be talking about the transformer architecture, and this is the backbone behind all the latest large language models that we know of, right? And we will be revisiting concepts from the "Attention is All You Need" paper, which is a paper from Google that introduces this architecture for the first time. And I will be splitting the entire discussion into two parts. Then this part will be focusing more on the self-attention mechanism and the different components related to tokenization, embedding, etc. So let's get started. So we'll be looking at a sentence completion problem. And one example is the following. So you have three words, cat is an, and you would like to predict the next word. Now to solve this problem, we will plug this entire sentence into a large language model. Okay, so that's a step. We plug this into a model that is based upon the transformer architecture, and we would like this model to output something reasonable. Now animal is a reasonable output for such an example. And this whole mechanism or this whole process can be easily carried out using a so-called decoder model. So the decoder model is usually used for such type of tasks. In addition to the decoder model, there is also something called an encoder model. So the encoder model can be used for tasks like name, entity recognition, etc. Or it can also augment the decoder model, and they both can operate in union. But I won't be complicating the discussion with the encoder architecture. We will be strictly limiting ourselves to the decoder model. Before we jump into the architecture itself, let's spend a few minutes looking into the different layers. To begin with, we have a sentence, right? And this sentence is supposed to be plugged into the model. So before plugging it in, we do something called tokenization that converts a language into numbers. This helps us to really create a link between the language and the model that only operates with numbers. Don't worry about the details for now. I will discuss them in the next few slides. So tokenization gives us a sequence of numbers, and this sequence represents the language that we have. Next comes embedding, that provides more semantic meaning to these numbers. So these numbers as such, as we will discuss later, don't really have much of a meaning encoded into them. So embeddings help us, infuse meaning into these numbers. And then comes positional encodings that help us encode the position of different words in our input sentence, which is shown here. Then we combine these two and plug them into the so-called transformer block, which contains several different elements. The first element is a self-attention mechanism. Self-attention is the mechanism via which the different components of a text talk to each other. And then after we have done self-attention, we do some normalization, followed by some very simple feed-forward network. This is your standard neural network, which takes in the input, and then the output is plugged into the normalization layer. We finally have the so-called softmax unit, which helps us generate output probabilities, and using these output probabilities, we are able to sample words that make sense. This is just an introduction. I will be discussing these different components in the following slides. Now, in addition to these different components, we also have something called residual connections, and they help us train deeper network. I will discuss this in the later lectures. And finally, the last component is basically a repetition of this transformer block several number of times. So as we keep on repeating these blocks, it helps us formulate richer and richer representation of language. So let's get started with tokenization. This is something that I already discussed in the previous slide. So we have a sentence, which in this case consists of three words. Our model, on the other hand, can only work with numbers. So the model operates in the background with matrices and vectors. So there is some form of a mismatch, right? On one hand, we have text, and on the other hand, we have matrices and vectors. And tokenization tries to connect these two worlds. And this is the whole idea behind tokenization. So how to basically link text to numbers. And one way to do this is to first construct something called a vocabulary. So the words in the vocabulary, you commit yourself to only worrying about the words in your vocabulary, and everything on the outside or outside of the vocabulary is thrown into a token called an unknown token, which is not shown here for simplicity. But you have a vocabulary, and then using the vocabulary you can order each of the different words alphabetically, right? So AB comes first, and then AN comes, and then you have cat, dog, kite, and is. So in this case you have only 6 words in the vocabulary. Usually this vocabulary would contain tens of thousands of words. Okay, and then we index these words based upon the location they have in the vocabulary. So AB is 0, AN is 1, cat would be 2, and so on. Okay, and once you have that, you can convert your text into a sequence of numbers. So cat is an is converted into the sequence 251. Now that's very good, because now we have a sequence or a vector which we can plug into the model, so we can start operating on these numbers. So this is one particular way of tokenization, and it's called word level tokenization. The other extreme is character level tokenization. So each character is an entity in the vocabulary. So in case of English, this could be the vocabulary would consist of 26 English characters. But what the modern day LLMs use is something in between. So you don't have a word level vocabulary, neither do you have a character level vocabulary. You have sub words in your vocabulary. For example, cat might be split into CA, ka, that might be one element of your vocabulary, and T might be the other. Now this vocabulary is built using specialized algorithm, and I think tokenization in itself is an entire video. So I will skip the details of the exact algorithm that is used to tokenize text in modern day large language models, and let's assume that our vocabulary is this limited 6 words, and this is our input, which is cat is an, and that's how it's tokenized. So this is tokenization, but tokenization has an issue. So tokenization doesn't have a semantic meaning. So what I mean by this is the following. So let's look at the following setup. So we have 3 words: man, women, and orange. And man has a token 3, women has a token 1, orange has a token 2. So now to capture the semantic meaning, or to understand how far away man is from the word women, I can just take a subtraction of the 2 token ID. In this example, what happens is when you subtract man to women, you get 2, and when you subtract man from orange, you get 1. So this indicates that man, the word man in the token space, is actually further away from women as compared to orange. So man is semantically more similar to orange than to women, which doesn't make much sense. So that's why when you tokenize text, you don't necessarily capture the semantic meaning, and this is what is being indicated here. So the difference between the 2 words can capture the semantic meaning, and in this case, we observe that tokenization doesn't necessarily encapsulates the meaning of different words. So what we will do next is to introduce an embedding vector. So instead of representing man with just one number, we would try to represent it with a so-called embedding vector. And so this embedding vector is d-dimensional, and it's good to remember this dimension d. So this dimension d would appear quite frequently throughout the slides, right? So d is the so-called internal dimension of the model, and every operation that we would perform would eventually lead to a d-dimensional matrix with a certain number of rows. Okay, so man now, the word man, is being represented by a d-dimensional vector, and this is the so-called embedding vector. And this has different entries, obviously, different entries that try to encapsulate the semantic meaning of man. And you can do the same for each different word in your vocabulary. So we'll do the same for orange. So when we represent orange, the numbers might come out to be this way. I will discuss later on how to compute these numbers or these embedding vectors. For now, let's assume that these vectors are given to us. So what happens now is, if you were to subtract man from the embedding of women, you will observe that these embeddings, they capture the semantic meaning, and this can also be concluded from the following diagram. So let's say we were to plot everything on a 2-dimensional space. Then you see that the embedding for man lies much closer to women as compared to that for orange. And likewise, the embedding for orange lies closer to the embedding for apple as compared to man, right? So we are able to capture the semantic meaning which is inherent in our language. So this is just one example of the semantic meaning that we were able to capture using embedding. There are other different types of relationships, much more complicated than the simple example, which one can capture using embeddings. Another great thing is, let's say you have a training set with a lot of references to orange and apples, but not a lot of references to banana. But because the embedding for banana is very close to the embedding for oranges and apples, your model will perform very well also when it sees the word banana, right? And this is because it has already seen in the text semantically similar words and their applications. So that's another benefit of representing words as embedding vectors, because you're able to generalize well to words that do not very frequently appear in the training data set. The same with the word gentleman. So now let's talk about how tokenization works together with these embeddings. So the way the embedding vectors interact with tokenization is through the embedding layer. And in the embedding layer, what you have is a embedding matrix, and that's what I've shown here on the right. So the embedding matrix contains the embedding vectors corresponding to each word in the vocabulary. So if you remember, our vocabulary was the following. It had 6 words. So so that's why we have 6 rows, and each row contains the embedding vector of each of these words. So the first row is the embedding vector for for ab, and then the second row for an, cat, dog, etc. So the way you would extract these embedding vectors is with the help of tokenization. So let's see how the process looks like. Our input is the following phrase, which only has 3 words. Each word has a particular token, 251 in this case, and then we would extract the corresponding rows from this embedding matrix. So for cat, we extract the third row. For is, we extract the last row, the 6th row, and we extract the second row. So basically, this then becomes our input to the model, these 3 rows. This is what I summarized in this slide. So what you have is an input of 3 words, and these 3 words are then converted into a matrix with 3 rows and D columns. Okay, so this is what we've done with the help of tokenization plus embedding. But what's missing, and that's a big part that's missing, is that we don't have any positional information. So we don't know whether cat is the first word, whether is the second word. So we don't know this relative ordering between different words. And to capture this relative ordering, we need to introduce something called positional embeddings. So this is what we do with the help of this matrix P. Okay, so this matrix P now has m rows. Each row corresponds to a particular word in your input sequence, and you have D columns, and the rows are defined such that all the different rows are unique. So basically the first row captures the first location, and that is entirely different from the second row, which corresponds to the second location, and so on. So I won't discuss the exact formula that we use to compute each of these elements, but this matrix P has no trainable parameters. Right? That's how it is very different from this embedding matrix C. So each of the element of the embedding matrix C is learned by the model, and it's learned while optimizing the cost function, which we will discuss later on. But each of the element in the matrix P, this is given to us. This is known a priori. It doesn't have any learnable parameters. So the way this is computed is with the help of sine and cos functions. I won't go into the details of how these functions look like, but you can check out the paper. They have the explicit expressions over there. For now, we will assume that we have such a matrix that captures the relative position between the different words. And what you do is eventually you just add them to the embedding matrix. So once you pass your input sequence, which is cat, is, an, to tokenization plus embedding, you get the matrix CM, and then to encode the positional information, you just add the embedding matrix to the position matrix. So C is added to P, and this then becomes the input to our model. Okay. So once we have the input to our model, let's give it a name. Let's call it X. So X is the input to our model, and the first layer, if you remember, was the self-attention layer, and this is what we're going to discuss in the next slides. So self-attention layer has many components. We will be discussing the first component, which is called the computation of value vectors. And you can see that I have decomposed X into different rows, and each row corresponds to the different words in our sequence. So the first row corresponds to cat, the second one to is, and then to an. And value vectors, what value vectors let the model do is that they're able to compute a richer representation of the input words. So this representation that we have in the form of X maybe is not enough. So we introduce another matrix called W, and that we multiply from the right. Okay, so X, when it's multiplied from the right by a matrix W, which is of dimension D cross D, we get the value vectors V. So these value vectors are just a richer representation of the input X, and it's very much possible that the model does not need to use any richer representation. In that case, this matrix W, which is to be fine-tuned, or which is to be computed during the learning process, will be close to identity, right? So all the parameters, all the elements of this matrix W are trainable, and it can happen that this matrix is just close to identity, in which case the value vectors will be very similar to the input X. So again, we don't. So again, we can decompose each of these rows into different words. So VMD has, by the way, the subscript denotes the number of rows and the number of columns each matrix has. So VMD means that we have a matrix V, which has m number of rows. That's the length of our input sequence. In this case, m is equal to 3, but it could also be greater or smaller than 3. And D is the number of dimensions of the embedding space, if you remember. And this D, as I told you before, will appear everywhere. This is the internal dimension of the model. So V is n times D. So each of these vectors, so V cat will be a d-dimensional vector, V is a d-dimensional vector, and likewise V an is a d-dimensional vector, all stacked on top of each other. But one thing that is quite clear from the computation of the value vectors is that we haven't made any of the words in the sequence interact with each other, right? So there have been no interactions between the word cat and the word is and the word an, and so on. And this, obviously, this is a great limitation to what we have done so far. So there is no interaction, and when you don't have any interaction between the different words, you cannot capture the essence of the language. So if you look at this expression that I have for vcat, it's also quite clear that we don't have any interaction between different words, right? So to compute vcat, all we did was we multiplied the input for X, we multiplied the input for cat, which is xcat, by the matrix W, and while doing this operation, we have no interaction whatsoever with X is and X an. So this interaction is missing, and this is what we will introduce next. This is what self-attention tries to do. So if you were to summarize self-attention in a very general form, you would say self-attention tries to capture the interaction between different words using the value vectors. Okay, and this is what we will discuss next. So how to capture these interactions. So what we have are different value vectors for each of the different words, and the easiest way to capture interactions between these words is to linearly combine them, and this is what self-attention does. Okay, so we will take a linear combination of the different value vectors, and this is basically the interaction that we've introduced. So we introduce now a new vector scat that captures the interaction between the word cat, is, and an, with some weights, which are denoted by a cat cat. So a cat cat denotes how much weight is the word cat putting on the word cat. Cat is denotes how much weight the word cat is putting on the word is, and so on, right? And we do exactly the same for all the other words. So s is, which is basically capturing the interaction for the word is as the word cat with some weighting, the word is with some weighting, and word an with some weighting. So one thing one should note is all these underlined terms. So all the terms which I have underlined, these are coming from the future, right? So in terms, if you look at cat is an as a sequence, then first we would enter the word cat, and we don't yet have the knowledge of is and an. So these two words will come in the future, and therefore this information is not really available to us when the word cat is input into the model. Therefore you cannot really use the and therefore for the generation task, you can't really use the information from these future words is and an. And when you would implement this decoder model, you would in practice mask these words, and that's why I've shown them with an underline. What does it mean to mask these words? You will just drop them. So these words which lie into the future, these words will be dropped out, and this can be easily implemented by using a mask. But for simplicity, I will continue with this form of attention mechanism, and this is the so-called unmasked attention. So you're not applying any mask to the way we are linearly combining information. Okay, so as you can see, this is also shown by this arrow. So all this information after this plus is into the future, and we would when we implement the decoder model, we will mask this future information, and we won't be using it to make decisions. Okay, so let's simplify this briefly. So let's collect all the weights in a matrix A, and this matrix would obviously be 3 cross 3 dimensional, or in the most general case, this would be m cross m dimensional. So if you have an m dimensional input sequence of words, then you will have m cross m entries. And now the question is how to compute these weights, because we already know how to compute the value vectors, right? That is something we've discussed already. The question is, how do we compute the weight? And as soon as you express everything in the form of this matrix A, you can easily conclude that this whole expression is nothing but a matrix multiplication. So you take the weight matrix A and you just multiply it by the value vectors V. Right? So as soon as you perform this multiplication, you get these expressions that we've written here. And probably it's quite clear to you, so that if you were to implement masked attention, you will introduce another matrix M in the middle that would implement the mask. Right? For now, we are just going ahead with the unmasked attention. Now the question is how to compute these weights A. And to compute these, we need to introduce two new vectors, and these are exactly the same as the value vectors. We'll introduce the query vector, which we represent by Q, and the key vector, which we represent by K. And we introduce these vectors for each word in the input sequence. So everything is exactly the same as we had for the value vectors. So nothing has changed really. Okay, and both of these vectors are d-dimensional, and the way we compute them is also exactly the same as the value vectors. So we have weight matrices WQ and WK, and we multiply them from the right to each of the inputs corresponding to the different words. So here we have xcat being multiplied by the weight matrix WK, and we have xcat being multiplied by the weight matrix WK. And this gives us the key vector. Here we get the query vector, and we do the same for each different word. So we get the query matrix and the key matrix. If you remember, this looks very similar to the value vectors that we computed earlier. Okay, so one thing to note is this W and WQ and WK. This is not the same as the weights we had for the value vectors. Okay, so these are different matrices. But all of these three matrices, WQ, WK, and WV, that we initially had, they are all three of them are trainable. So this is something that the model learns from the training data. So then the question is, how can we use the query vector and the key vector to compute these weights that we discussed about, right? And one way to do this could be to take the inner product. So if I want to understand how much weight should I put between the two words cat and cat, one thing I can do is just take an inner product. So basically, the query vector and the cat vector is capturing the inner product between them, is capturing the weight between the two words. And you can do the same for other words as well. So you can do the same for cat is, you can do the same for cat an, you can do the same for is cat, is an, and for all the different words that we had. Right? So we can represent the weight between words using the inner product between the query and the key vectors. And now we almost have the expression for the weights. Only one thing is missing, and that is some form of normalization. So the thing is, these weights that we introduced earlier, they need to satisfy two properties. First of all, for each of the words, right, the weights need to sum up to 1. So we are taking a weighted sum, and we would like the weights to sum up to 1. And secondly, the weights need to be positive. Right? It doesn't really make much sense to have weights which are negative, and these two properties are not satisfied by the values B that we introduced here, right? So B, it can be negative as well. It's just the inner product between two vectors, and that could very well be negative. And secondly, the sum of these B's corresponding to each different words, doesn't need to be 1. So the sum can be anything between -infinity and infinity. So both of these conditions are not satisfied by taking an inner product. Now to satisfy these two conditions, we introduce a softmax function. Okay, so what a softmax function does is as follows. So you have first an exponent function. So it just takes the exponential of the dot product we computed, right? That's shown here. As soon as you take the exponential, what happens is that you satisfy the second property. So exponential function is always positive, and therefore we have a weight which is positive. Now to satisfy the second property, we just multiply by the sum of all the different weights. Okay, we divide by the sum of all the different weights. And as soon as you make this division, right, the summation property is satisfied. So this thing here, so there are two steps to remember. First is the exponentiation. So when you exponentiate anything, you get positivity, and that's how you satisfy the second property. When you divide by the sum of each of the weights, you enforce the first property, which says that the sum of the weights should be 1. Okay, so you do this for every different value of b. Okay, so once you have this, you have the weights that you were looking for in the self-attention layer. Okay, so let me just summarize things and make them a little bit cleaner and reconcile them with the publications we have. So let's say we collect these inner products in a vector b. So b cat contains all the inner products corresponding to the word cat. So we have b cat cat, b cat is, and b cat am. And then we apply softmax function to b cat. So softmax is nothing but this operation. So both these expressions are equivalent. And then we can express everything in the form of a matrix vector, in the form of a matrix product. And let's do that. So we have 3 different weight vectors: a cat, which is softmax applied to b cat; a is, which is softmax applied to b is; and a am, which is basically softmax applied to b am. Right? It's exactly the same as what we did for cat. We did the same operations for the other 2 words. Next, we take the softmax out. So we summarize all these different b vectors in a matrix. So b cat comes first, b is, and b am, and we took the softmax out. But when you take it out, we give it a subscript 1. This denotes that we're taking softmax along the first dimension. That's along each of the rows. Okay, and this is important. We're normalizing for each of the different words separately. Right? This is what the condition is also telling us. Okay, so we've taken the softmax out. And now when we replace the different b values by inner products, so let's say, so the inner products were taken between the query and the key vectors, and that's what we've done here, right? So we've replaced all the different b values by the inner products between the query and the key pairs. And as soon as you do that, something great happens. So you can write this whole expression as a product between the query matrix Q and the transpose of the key matrix K. Okay, so that's the expression that you usually see in the literature, right? So there's a weight matrix. The weights that we had, which we were using to linearly combine, are nothing but softmax applied along each row of the Q times the K transpose matrix. And I can summarize this in the next slide. So let's look at the summary. So we wanted to linearly combine the information between different words, because that's how we introduced interactions between different words. And how did we do that? We did that by taking a linear combination between the different value vectors corresponding to the different words. So that's what I have recalled here. So you have the interactions for cat, where you took a linear combination between the cat value vector, the is value vector, and the an value vector. And you likewise have a linear combination for the word is, and you also have the same for the word an. Okay, then we represented it as a matrix. So as soon as we collected all the weights in the matrix A, we could formulate this linear combination as a multiplication between the weight matrix and the value vectors contained in the matrix V. And then we introduced a query matrix Q and the query matrix K, and using the inner product between these 2 matrices, we captured the weights between the different words. So these 2 matrices are very much the same as the value matrix. The only thing that was different was we were using different trainable parameters for these three matrices. But the dimensions of these trainable parameters were the same, and the way they were multiplied by our input were also the same. You can also observe a new parameter, or not a parameter exactly, but a new normalization factor under square root of m. This normalization factor controls the variance of this whole weight matrix. Right? So one can show that if q and k, they come from a standard normal distribution, then the variance of this term scales as m. So that's why you divide it by square root of m, hoping that this would help you control the variance and the variance would not blow up. So that's the output. That's the final output of our self-attention layer. So self-attention layer is creating interactions between different words, and the way it's doing that is by first computing a richer representation of each word, which we have of each word. And so it's doing that by first computing a richer representation of each word, and that's done using the matrix V. And then it's computing the weights using which a linear combination is constructed. And these weights are computed using the matrix Q and K. So the final output from the attention layer is again then multiplied by a projection matrix WO. So this matrix again, this helps us generate a richer representation of these linear combinations. But one thing you should note is we're not introducing any interactions between the different words anymore. So whenever we multiply by the weight matrix from the right, we are not enforcing, or we're not introducing any interactions between the different rows of the matrix S. So this operation again is very similar to what we did earlier. So that's the output from the self-attention layer, and the next video I'll discuss how this output then is passed along through the different layers to create the output that we're looking at.